Everyone has to obey the laws of physics, even if you're the king. The power to make night into day, create life, or cause death. This is all part of the mystery and magic of electricity. Long before we knew what it was, long before we harnessed it, electricity was flowing through our bodies, descended from the heavens.
So there's constantly current flowing into the earth from thunderstorms and flowing out where there's not thunderstorms. And in that process, an electric field is generated in the atmosphere. We walk around, the voltage between your head and your toes when you walk around is 200 or 300 volts, and nobody notices that because you grew up in it.
But when there is enough of a voltage difference between the clouds and the earth, it's hard not to notice. One of those who was fascinated by the phenomenon was Benjamin Franklin.
Ben Franklin was a really smart guy. He was one of the original experimenters with electricity, period. He, in fact, invented the designation of positive and negative charge.
Today, high technology has replaced the kite. In north-central Florida, scientists summon lightning and bring it to the Earth with a rocket and a wire.
We can make the cloud produce lightning and direct it where we want to direct it to do tests, and that really hasn't been possible before.
They direct the lightning to strike simulated houses and power lines to understand what happens when it hits. The rocket launch provides a more controlled experiment than anything Ben Franklin could have imagined.
Well, we do similar things. He didn't think his kite was going to get struck, and he thought that if it was going to get struck, that he wouldn't get hurt. So he was wrong there. If the kite had been struck, he probably would have been killed, as have many people flying kites.
They load a rocket and launch it into the belly of a thundercloud. From the rocket's tail, a spool of copper wire unwinds, creating a path for the lightning to follow.
There's a level of excitement and tension before you push the button, and then there's a level of holding your breath for 2 seconds when the rocket goes up that's unlike anything else. And success feels real good because we only make it happen 20, 25 times a summer, so every one is a big deal.
It's like a rocket-powered lightning rod. Once the wire is shot up into the air, the lightning hits it. In an instant, the electric current of the bolt moves down the wire, disintegrating it into a green vapor.
What flows down the lightning at 50,000 amps is the same thing that flows in your wall at 10 amps.
The temperature of a lightning bolt is more than 50,000 degrees Fahrenheit, 6 times hotter than the surface of the sun. All that heat and light is generated by uncounted numbers of electrons being forced to move. An atom's nucleus has a positive charge. Electrons orbiting the nucleus have a negative charge. When electric current flows, electrons are torn from atoms and move freely.
Electricity is the flow of electrical charge, and most of the charge flows as electrons moving.
Whenever there's an oversupply of electrons, an object develops an overall negative charge. Nature balances things out with equal positive charges somewhere else. The potential difference between the charges is measured in volts. Electric current, anything from static electricity to lightning bolts, is electrons moving from negative to positive.
It seems like it's easier to make sparks and lightning than not to make them. Anytime you have two dissimilar materials rubbing together, you get sparks.
The path that leaping electrons follows depends on the material they flow through.
The human body certainly will conduct current, but not a lot. Not like a piece of copper.
Copper has a lot of loosely held electrons, so it's a good conductor. The electrons of clay and rubber are too tightly bound to their atoms to conduct electricity. They're said to be insulators. How electrons begin to move in the first place is a result of a force of nature called electromagnetism. Our whole technological civilization exists because electricity can make magnetism, and magnetism can make electricity.
It goes back to the fact that we have two kinds of forces that are present that we call electricity or electromagnetism. And those two forces are the electric force and the magnetic force. The fundamental charges are a positive charge and a negative charge.
To see these forces at work, head north and look up into the night sky. Basically, the northern lights are the result of high-energy electrical currents from the sun that are caught and guided by the Earth's magnetic field. There's electricity out there.
5, 4, 3, 2, 1. And we have liftoff of the Space Shuttle Columbia, continuing space research through tethered satellite technology.
On February 25, 1996, NASA and Italian researchers made a bold attempt to harness the power in the atmosphere. They generated electricity with a satellite on a wire.
Good work. Let's make sure we stay that way. Understand.
The mission was part of a new experiment of tethering satellites in space.
Attitude verification, 3-14. Go ahead.
The experiment was based on the simple principle that when you move a conductor through a magnetic field, electrons start to flow. This generates an electrical current that can flow through a circuit. The satellite was thrust into space using small gas jets, and the 13-mile-long cable began to unreel.
If you put a wire inside of that tether, you now have a moving wire that moves across a magnetic field. That magnetic field in this case is the Earth's magnetic field, and the motion is the motion of the space shuttle moving at very fast, high velocities, orbital speeds.
Things look fine down here, Jeff.
The moving wire in the Earth's magnetic field generated 3,500 volts, enough energy to power a space station.
Okay, we see the tension go way down, but the tether's still going out fine. Very slight lateral oscillation.
The tether was clearly visible from the ground. It was one of the biggest man-made objects ever sent into space. For 5 hours, the tether swept through our planet's magnetic field, generating more and more electricity.
At the boom. The tether has broken and is going away from us. Get it on the TV, Claude. Please get it on the TV. The tether has broken.
Copy.
photograph it floating away from us.
Looking back, we quickly saw that, in fact, the tether had broken. This was it's a big shock. It's kind of an empty feeling in the pit of your stomach when you look and you realize that there is the tether moving away from us at about 80 feet per second, and you just wanted to reach out and grab it.
The wire was generating so much electricity that a spark jumped from the wire to the satellite deployment system and burned through the tether. The $440 million experimental satellite just drifted away.
Yes, sir. Well, those are some tether dynamics we did not want to see.
Well, we have demonstrated that you can generate a lot of electricity with tether, and unfortunately we've also demonstrated that you can use tethers to launch a satellite into a much higher orbit.
NASA will try the experiment again because it could lead to a new, more reliable power system for space stations and help avoid situations like the Mir mishap.
We're moving to actually is if we drive current in the opposite direction in the tether and if we can force the current to go the other way, it becomes a propulsive device. So a propellantless spacecraft, the next generation of space travelers may be using electric propulsion devices as opposed to chemical propulsion devices. A little Star Trek, if you will.
Perhaps we notice electricity most when we don't have any. On July 13, 1977, New York City experienced a blackout. For 25 hours, New Yorkers were without lights or elevators or alarms. Lightning had knocked out power lines north of the city, and the utility company's backup equipment malfunctioned.
It takes a lot to keep the electricity working, not just in machinery, but in manpower, and it costs a lot of money to maintain these systems. The utilities have to maintain their lines.
In the United States, 98% of homes and businesses receive power from a vast electrical system that is woven together with a web of power lines. A grid. These power lines are naked live wires, carrying 500,000 volts. It's up to the lineman to inspect and repair every part of the grid, usually without shutting down the power.
And Bill, I was going to start making a gradual left turn and start heading over towards the line.
One of the most daring techniques is used on very high voltage tension lines.
It's pretty dangerous, I feel, because you're mixing aviation with electricity. One, you're depending on the helicopter, everything mechanical to go right. If it goes wrong, you're going to drop out of the sky like a rock. If the lineman makes a mistake, you're going to vaporize.
These linemen and pilots work for AgRotors Incorporated. One of the few companies that attempts these high wire acts, AgRotors has the best safety record in the business. It's dangerous work that only a handful of people in the world are qualified to do. One of them is Spider Lockhart.
Because I'm going to put the hood over top of my helmet.
The dress required for the job is a lightweight suit of armor made of stainless steel thread.
We have a strap on the inside that ties to the pants, making an electrical connection between the pants.
Electricity follows the path of least resistance. In this case, the metal threads of the suit, rather than flowing into the body of the worker.
We're dressed in a stainless steel suit, fully conductive, fireproof, Nomex. Everything we have is fully conductive.
Have you ever walked through a hotel room with a certain pair of sneakers in the wintertime where you walk up to your hotel room door, reach over and grab the door, and you get a little zap on you? That's called static electricity. Basically, that's what I'm trying to eliminate from what I'm doing.
There's linemen all over the United States that are risking their lives every day to keep the power flowing.
The dangerous marriage between helicopters and power lines is made to save money and time. Repairs that take a conventional ground crew days, Ag-Rotors completes in hours.
And Bill, we're just looking for the right structure number, and then we're going to have to probably turn back a span or two once we orient ourselves.
The lineman's life depends on constant communication between him and the pilot.
This is the span that we want. I'm going to go ahead and come down in between the two 500 kV lines, and we're going to find the damage location, and we'll get ready to start work.
We could actually get too close to a power line and a tree, and the electricity would arc amongst all of us, and we could actually short out the power line and destroy ourselves.
Both men know if the communication stops, something is wrong. It's a crucial fact that Spider Lockhart learned from experience.
As soon as I felt the voltage going through me from the mechanical ground that I had, I knew that I'd made a mistake. Sometimes it's a little bit late to figure out your mistakes, but I knew that as soon as I felt that. I had enough to know that it was killing me, and that's, to me, I was screaming to the pilot to get me away from the wire, and he never heard a thing because I couldn't open my mouth.
The electricity stopped Spider's heart, but a co-worker revived him, saving his life.
And I saw Spider laying across the platform, half on, half off, and I knew something was wrong. When the helicopter came in, I didn't even wait for it to land. I jumped up on top of it. I started cutting his body harnesses off of him. I closed his eyelids, and I just started giving him CPR. And I worked on him a little over 3 minutes before I brought him back.
When Spider is suspended in air and therefore not grounded to anything, the electricity treats him as part of the wire and safely passes over his body and not through it.
If you were able to take a voltmeter, which measures voltage, and measure the voltage on that helicopter, it would be energized at 500,000 volts in anything on that helicopter.
The metal wand gives the electricity a controlled pathway from the wire to the helicopter. Once the pathway is established, the lineman replaces the electrical connection held by the wand with metal clamps. The clamps allow the lineman to free his hands so that he can work.
I was working in the middle of the Everglades, and I knocked the bond off, unbeknown to me. And when I went to get close to the wire, the arc went straight to my mouth. So I absorbed roughly about 500,000 volts to my mouth and my nose, blew all the fillings out of my mouth, cauterized my nose, knocked me out of my seat belt up underneath the platform, the belly of the ship on the platform. And I was unconscious, it seemed like, for a pretty long time, but it was just a few seconds.
The amount of voltage may be the first fact recited when explaining the dangers of electricity. But the high voltage isn't what kills a person, it's the amps. The electricity in the lines can flow at 500,000 volts, but isn't necessarily deadly if the amps are low. Real low. It only takes 1 amp to stop the heart. Think of the electricity flowing through wires as the flow of water. In a squirt gun, water is under pressure and moves fast, but to put out a fire, it's not the best choice. You need a fire hose that can move a whole lot of water. The water pressure is equivalent to voltage and electricity. The amount of water is like electrical current and is measured in amps. Electrical measurements are based on numbers of electrons. A light bulb, which uses 1 amp of current, has 16 quintillion electrons moving past a single point in the wire each second. And they all have to come from somewhere.
Good evening, ladies and gentlemen. My name is Bruce. I'm going to be your guide for the tour this evening. Behind me is Hoover Dam, 726 feet tall and 660 feet thick at the base. Hoover Dam contains enough concrete to pave a two-lane road from San Francisco, California to Miami, Florida. Ladies and gentlemen, while you're on tour this evening, there are a few rules which you are going to have to follow. If you hear bells, whistles, horns, sirens, or buzzers, look at me. If I'm still standing here, it is not an emergency. If it is an emergency, follow the instructions which I give you carefully. Don't trample me trying to escape. I have the keys.
Hoover Dam is one of the greatest civil engineering feats in the world. The dam is more than 700 feet high, forming a lake more than 100 miles long. Its purpose? To turn the energy of falling water into electrical energy. This accomplishment was made possible by the labor of men like Tommy Nelson and Lee Tillman.
We didn't have time to think about anything too much other than we knew we were going to get paid at the end of the week. Wasn't very much money, was it, Lee?
No, in my case, it was $5 a day.
Yeah, you did better than I did. I was only making $4.
Yeah, well, I was driving a truck.
Yeah, but you were driving a truck.
Yeah,
that's true.
Yeah, so they give me another $1 a day. Yeah.
Hoover Dam was built during the Great Depression of the 30s. It not only created badly needed jobs, but was also part of a nationwide effort to transform rural life through electrification.
We went from kerosene lights to carbide lights, propane lights, and finally here comes electricity, and it's available to everybody. Rural electrification. Franklin Delano Roosevelt, he did a great thing for the West.
Today, Hoover Dam alone generates enough electricity to serve more than 1 million people. That's a lot of watts. Multiply volts times amps, and you get watts. It takes 100 watts to light a bulb. 1,000 watts equals 1 kilowatt. Hoover Dam produces 4 billion kilowatts a year. Electricity that's sent to California, Nevada, and Arizona.
This is the Arizona wing of the power plant. This room is longer than 2 city blocks. We have 9 of our commercial generators in this wing, each producing 16,500 volts of alternating current. Each generator can supply enough electricity for a city of 100,000.
The power of falling water spins the blades of a turbine. The shaft from a turbine spins a magnet inside a tightly wound coil of wire. This motion generates electricity. The spinning magnet causes electrons to move in the wires and produce an electrical current. In this case, it's alternating current.
A direct current flows directly without any pulsations. It's just a direct current. It's exactly what it is. It's like if you open a pipeline and let the water flow in one direction. That's direct current. And the word direct means just that, and that's exactly what it is. Alternating current means that the electricity flows to the load and back to the generator, to the load and back to the generator, and the frequency that this happens is called cycles.
The generators produce 16,500 volts of electricity. Before it leaves the power plant, the electricity's voltage is increased or boosted to 230,000 volts for long-distance travel. At the other end of the line, the process is reversed, and the high voltage is stepped down to 110 volts and delivered into millions of homes. In some places, the need for electrical power has forced people who can't afford it to break laws and become electricity rustlers. In the shanty towns of Rio de Janeiro, Brazilians who are unable to pay for electrical power learn how to tap into the grid for free.
Bom, eu levo o fio da ligação da minha casa I take wire from my house up to a clock or a light post, and from there I bring in the electricity.
Electricity is siphoned from main lines and tangles of makeshift wiring. Live wires and unsafe connections are hazards that the local people live with, or in some tragic cases, die by.
Horrível porque ele não sobreviveu. Ele foi fazer uma ligação.
It was horrible because the electrician pirate didn't survive. He was making a connection for a lady whose house had had a blackout. He had been in the water earlier, so he was wet. He climbed on a zinc rooftop and started touching the wire. He got a strong shock and was thrown from the spot and died.
These self-taught electricians are often regarded with gratitude by residents.
Isso é horrível. Sem luz é horrível.
I'm not a hero, but there is a risk. I sometimes talk to people from the electric company, and they teach me how to make connections, so I don't get caught. It can be dangerous.
Ninguém vê nada.
Today, life without electricity is unimaginable. Las Vegas.
Well, people are like insects. They just love light, and they're drawn to it, and they want to see what it's all about. And so the casino operators and everybody here put a lot of light out, and it just draws people in. It just says, we're having a party here. Come on in. Come on in.
In Vegas, the theory is, if you build it, they will come. And if you build it and cover it with lights, they will come and spend money.
Without electricity, this town would just be another sleepy place in the desert.
From space, it's the brightest man-made spot on the planet. Millions of bulbs that all, at one time or another, burn out and need to be changed. Every night, crews from the Young Electric Sign Company go to work repairing and replacing bulbs. One of their biggest jobs is the Fremont Street Experience. On a grid above pedestrians shine 2 million bulbs and a $70 million light show. The town never shuts down, but things are a little slower after midnight. That's when the crews test the system and make repairs. It's Homer King's job to change the bulbs.
That way the computer will tell it how bright to go. These bulbs have a life expectancy of 25,000 hours. I'm on a roll tonight here.
A light bulb lights because its filament offers some resistance to the flow of electrons.
Okay, that looks better.
As the electrons try to crowd through a hair-thin tungsten wire, the energy spent overcoming resistance turns into heat.
A material that's resistive is one that requires some kind of work to push the charge across. That means you're giving up energy that turns into heat and will heat that element up.
And here, heat means light. The filament reaches a temperature of about 4,500 degrees Fahrenheit. On Fremont Street, the bulbs burn bright. 7 shows a day, 7 days a week. And nothing stops the display, except for thunderstorms.
We'll run this color for about 10 to 15 minutes. People ask us all the time, does this keep rain out? Well, no, it doesn't keep rain out. Water doesn't really hurt it. What hurts us is lightning. We got 30 computers on the other side of this frame. So when the lightning's there, we shut it down.
The Fremont streetlights are controlled by 121 computers. It's the largest outdoor sign in the world, towering 90 feet high and spanning almost 5 football fields.
Hard Rocks, this is one of my favorite properties here.
Not all the lights in Las Vegas rely on bulbs. Neon and fluorescent lights use electricity to excite atoms that do the glowing, instead of heating up a thin wire. The signs may change, but using light to attract crowds has been around since electricity was harnessed. Coney Island was one of the very first places to use electricity. Thomas Edison lit it up with 1 million of his new incandescent bulbs. They called it an electric Eden.
Being, I guess, like almost like a new world. It was like the playground of the world, and being all lit up.
At the turn of the century, Coney was the largest amusement park in the world. Charles Dickens, Mark Twain, Sigmund Freud, Herman Melville, and Walt Whitman were among the thousands who flocked to see the magical electric light at work.
Coney Island wouldn't be Coney Island without electricity. If you remember correctly, electricity made its debut in Coney Island.
Coney is lights, Coney is movement, Coney is electric. The electric Astroland Cyclone is ranked one of the top 5 roller coasters in the country, and it is one of the oldest. By the time it reaches the bottom, it's traveling 55 miles an hour. And the passengers feel the force of 4 Gs. For the last 70 years, this electric motor has made it all possible, pulling the 7-ton car to the top of the hill. An electric motor is a generator in reverse, turning electricity into motion instead of the other way around. The motor is connected to a belt that turns a 15-foot wheel that pulls the chain. It's a powerful system. When the roller coaster clanks up the hill, the motor is drawing 600 amps, enough electricity to power 3 modern homes. Coney Island was one of the first places that exploited electricity for profit and pleasure.
Good use. It's the only use. I mean, listen, electricity, it attracts us all. If we didn't have electricity, where would we be?
Along with the rest of New York City, Coney Island found out what it was like to be without electricity in the blackout of 1977.
All of a sudden, lights went out, and I looked out at the park and up at the Wonder Wheel. Nothing was moving.
As soon as scientists were able to capture electrical energy, they began to experiment with it. In 1780, an Italian anatomist, Luigi Galvani, made groundbreaking discoveries.
Galvani made lightning measurements. Galvani took frogs' legs and showed that when it lightened, they twitched. So he showed that the lightning radiates an electric field which produces a voltage on the frog legs.
Throw the switch. Wait, I thought
I saw a pulsation of the heart. You're right. Dr. Bradshaw is beginning to breathe. You've brought this man back to life.
No. The heart muscle has simply responded to a terrific electrical shock, that's all.
What was once thought to be science fiction turned out to be fact. A heart beats because every second electrical impulses spread through the heart muscle, triggering and coordinating a movement. These signals send echoes through the body tissue to the skin, where they can be detected by metal sensors and displayed as an electrocardiogram, an electrical readout that allows doctors to constantly monitor the heartbeat.
Electricity and electrical impulses are all over the body.
The electricity in our bodies is created by chemical reactions between cells.
What triggers the heart to squeeze are these signals, these small electrical currents, which travel from the outside to the inside of the cell every time your heart beats.
Dr. Hugh Calkins is an electrophysiologist at Johns Hopkins University. He uses electricity to treat and cure electrical malfunctions of the heart. Today, he is implanting a device in a patient who suffers from a condition that causes the heart to beat too fast.
It takes a certain amount of time for the heart to squeeze blood out of the heart, and also for blood to get back into the heart. So if you go very, very fast, instead of squeezing in a rhythmic fashion, it will literally be quivering, and no blood will flow in the body, and within seconds you'll pass out, and in minutes after that you'll be dead.
In order to restore the heartbeat, the victim needs an electrical shock.
When you just put these on the body, you get what's called a quick look, that this acts as an antenna. You can see what the heart rhythm is, and if it's not what you want it to be, if it's ventricular fibrillation, then you can go ahead and discharge it. The way that's done is by pushing both of these buttons simultaneously will cause these to fire, and that will give a 360 joule shock across the body. And to the degree that the heart's in between, the heart will be depolarized and normal rhythm will be restored.
In the electrophysiology lab, the technology of portable defibrillators is now being implanted in the body. Calkins threads a small wire lead down into the heart.
That's up in the pulmonary artery.
The wire lead acts like permanent paddles on the heart. If the implantable defibrillator detects a problem, it will automatically give an electrical shock to the heart within 10 or 15 seconds.
When I put one of these in, you really have this comforting sensation that this patient, it's like as if they're in the intensive care unit forever, that if ever they develop a rhythm abnormality, too slow or too fast, it will take care of it. And it's really this tremendous insurance policy.
The most critical part of the procedure is the testing of the device.
Here we go.
The patient is given a shock that puts his heart into overdrive. The heart starts fluttering rather than beating steadily. Ventricular fibrillation, they call it. Sudden cardiac death. It's the only way to test the device.
When we were putting in the defibrillator is when we induced this ventricular fibrillation, this very fast heart rhythm. You saw a lot of very rapid squiggles on the screen, and that was the heart beating very, very chaotically with multiple short circuits swirling around the heart, resulting in the heart beating 400 or 500 beats a minute. 10 joules, which is about 500 volts. Yeah, this shows the whole readout from how we induce it with a shock. And this is the VF. And it takes, you can see, about 8 seconds for the device to charge up and get them out of their rhythm.
The trick is to customize the implantable defibrillator so it delivers the lowest level of energy that can still get the heart beating back to its normal rhythm.
There's more and more enthusiasm about the benefits of electricity. I know for many, many years there was a lot of debate over was it better to treat patients with sudden cardiac death with medications or with defibrillators. And now the studies are available showing that defibrillators are better than medications, at least the medications we have now. So there's a case where electricity won, where electricity was better.
This is a Utah arm, one of the newest links between human and machine. The device uses the body's own electrical impulses to operate and control an electrical arm. John Migueles works with amputees, teaching them how to use and operate the myoelectric arm.
Right now there's a race between limb transplant and electronics. We start off with a silicone skin, and inside it there are electrical motors that control the opening and closing of the fingers. Next, very often we have a electrical motor here that operates wrist rotation, supination or pronation. Then we also have an electrical motor over here that controls this transmission that you can see that controls flexion and extension of the elbow. The microcomputer is mounted right here, and that processes all that information. One of the neat things about the hand is it offers a lot of pinch force, over 22 pounds of pinch. So we need to be very careful when we're grasping things.
Bob Goodman controls his bionic arm by contracting his biceps and triceps muscles.
I like to grab my brother's hand and squeeze it and kind of watch his eyes a little bit. Maybe that's a little bit of bionic feeling.
Ironically, it was electricity that destroyed Bob Goodman's arm in the first place. He was up on a roof removing a television antenna when something went wrong.
This antenna became top-heavy and came in contact with high voltage lines in back of us, some 12,500 volts. It was an aluminum ladder that I was on, and so it became very hot and burnt my leg. Luckily, I was knocked loose of the ladder and hit the ground, because some of the doctors think, well, with that amount of volts, your heart probably did stop. When I hit the ground, it kind of jump-started my heart again. So I felt very fortunate when I learned this, that I got a second chance at life, even though I was missing my right arm.
When the brain sends an electrical signal to flex the arm muscle, the signal, or impulse, is intercepted at the muscle site by electrodes, or skin sensors. This electric impulse is then amplified and used by a microcomputer to control the electrical motors in the arm.
The patient has to be able to produce two independent signals, or muscle contractions. Typically with Bob in this situation, we're using biceps and tricep muscles, but he has to be able to fire those independently. If he were to fire them together, it would tell the hand to open and close at the same time, which would just create a little jitter in the hand.
In a myoelectric arm, when you lock the elbow here to make the hand work, to unlock this elbow, it takes the flex of both muscle sites at the same time and then an instant relaxation. So for me to get that elbow to unlock, it took quite a few months actually. I would always flex one site before the other. So it was releasing the elbow is what took me the most time to get down.
So how are things going? You having any particular problems?
Not really. I've put a new harness on and snugged up the fit in my socket, so it seems to be responding really well.
Great. How's that battery doing?
Well, I'll turn this arm off here, and the batteries are holding up real well. This new battery pack is lasting 4 to 5 days for me. A lot.
Okay.
It's opening and closing the same amount of effort for both. Open this and clean this.
Okay. Open and close? Good. Close? Great.
When I first tried it on, I think there was a hint of having an electrical arm this close to my body, but as soon as I was able to make the arm work and the hand to work, and that all disappeared. I thought it was so neat that a person could make a lifelike hand work so effortlessly that fright left right away. It became more of an enhancement than a threat right away. been releasing real well.
A Utah arm can cost anywhere from $45,000 up to $120,000.
Stuff the lights on, which means that
I've chosen to wear this arm every day, so maybe I didn't learn quite enough lesson from an electrical shock because I still wear an electrical arm.
Okay. Good for another 10,000 miles.
Yeah, good.
The modern world would be inconceivable without electricity. In 8 hours, a man used to hard work can continuously exert 1/10 of a horsepower. But the same amount of work can be done by an electrical motor in a fraction of the time. Electricity as a harnessed power has no rival. It is clean, silent, and can be turned on and off instantly. Worldwide, there are still 2 billion people who exist without electrical power. Most are located in remote places like the Brazilian village of Boa Sorte. Too isolated to receive power from the country's grid, the residents did without the electrical inventions of the 20th century. And without conveniences like medical vaccines that need refrigeration. Electric motors, or clean running water. The villagers used contaminated surface water, which was funneled from the springs to the local watering hole. The only clean water was buried deep beneath the earth. An electrical pump was needed to get the water to the surface. To solve this problem, the governments of Brazil and the U.S. joined forces to provide electricity by harnessing the sun's energy.
Putting out power poles and lines is so expensive that actually photovoltaic energy is much cheaper here than using traditional forms of fuel.
Photovoltaic cells, or solar panels, convert energy radiated by the sun into electricity. Clean, renewable power that villages like this can afford. Engineer Roger Taylor is part of the electrification initiative in Brazil.
In this particular village, they're going to change by having the school accessible at night. The health clinic will certainly be able to store vaccines and provide more immediate health services. And the water pumping system here, particularly since it's so deep, will provide very pure, very clean, filtered water.
The joint effort will set up 4 different systems here. The largest will power an electric water pump for the well.
Water pumping takes a fair amount of energy in this case because the well is fairly deep. The well here, we will put the pump at about 100 meters down in the ground, so it takes a lot of energy to pump that water up to the top.
When a solar panel is put out into the sun, the materials within it release electrons and produce electricity. In Boa Sorte, the panels are being connected to a pump. When the system is up and running, the electric current and water will flow. On May 26, 1997, the village turned on the power. Technological advancements that took 100 years to develop arrived here with the flick of a switch.
And so then it would be very interesting to see, once they have the basic standard of living that many people in the rest of the world enjoy, how their lives and their culture will evolve from that.
More and more aspects of our world depend on electrons in motion. They flow through countless switches and machines. They flow through our bodies and brains. They can even start life.
In a test tube, you can make lifelike things, molecules, with electric sparks.
When researchers in Scotland cloned a sheep named Dolly, a tiny spark of electricity was used to fuse cells and start the egg growing into an embryo. All this started with a curious fellow back in 1752. That was when a man with a key and a kite stepped out into a storm. He snatched lightning from the heavens and introduced electricity to mankind.